Welcome back everyone. We can discuss some more gate and net questions based on the topic number system. So the first question is the hexadecimal representation of 657 with base 8. A base 8 number is given. We need to find its equivalent hexadecimal representation. Okay, so in our previous video we have already discussed similar examples for getting the hexadecimal representation of a base system. What we want to do, we need to take its binary equivalent first. So this is a base 8 system. In a base 8 system, for representing each symbol uniquely, we need minimum 3 bits in its binary. Right? So using 3-bit combination, we can write its binary equivalent. 7 is represented using 3-bit as 111 and 5 is represented as 101 and 6 110. Okay, so directly now we have this binary equivalent of this base 8 number 657. We need to get the hexadecimal equivalent. What we want to do for getting the hexadecimal representation of a binary pattern, we need to make different groups. Each group must contain 4 bits. So start from our right hand, proceed towards left and make different groups of 4 bits. So 1, 1, 1, 1. These 4 ones together form one group. Next 1, 0, 1, 0. These 4 bits form another group. And here we have only one single bit. That is, a single one is left over here. In that case, we can append 3 more 0 to the left hand and make it as a group of 0, 0, 0, 1. Okay, so we can directly write its hexadecimal equivalent. 1111 as F in hexadecimal form. 1010 is A in hexadecimal. 0001 is 1 itself. Now we can arrange this hexadecimal equivalent in order. 0001 is the first MSB position, that is 1 first. Next 1010 which is A. Next 1111 that is F. So this is the hexadecimal equivalent of this given base 8 number. Next question. Perform the following operation for the binary equivalent of the decimal numbers -14 plus -15. We need to add two decimal numbers, -14 and -15. The solution in 8-bit representation. We need to get the result of this addition in binary form and in 8-bit representation. Okay, so here our task is an addition over two decimal numbers -14 and -15 and we need the result in its 8-bit binary form. So we can perform the addition directly. So while adding these two negative numbers in decimal, we get -29 in decimal. Next task is to obtain its equivalent binary form. Here we need the binary of -29. How it possible? For getting the binary of -29, we need to take the 2's complement form of binary of +29. 2's complement of the binary of +29 is actually the binary representation of -29. Once more, the 2's complement form of binary of +29, which is equal to the binary or the 2's complement representation of -29. Okay, so in order to get the binary equivalent of our result -29, what we want to do next, we need to take the binary form of +29 first. like this. Okay. So after dividing this 29 continuously using the divisor 2, we get the binary 11101. So this is the binary equivalent of positive 29. To get the binary equivalent of minus 29, we need to take the 2's complement of this. Right? We need to take the 2's complement of this. How to get the 2's complement of a binary number? 2's complement is 1's complement plus 1. Right? We have one more method, that is a direct conversion of a binary to its 2's complement form. How it possible? For that, we need to start from the right end and scan towards left and write everything up to which the first one is encountered. And after that, all other bits we need to complement. That is the direct method for getting the 2's complement of a given binary number. Once more, we need to start from the right end and proceed towards the left end and write every bit as it is up to which the first one is encountered. After that, just take the 1's complement of all other bits. Based on that, the 2's complement method of this number, this binary is, in the first, we need to start from the right end and proceed towards left. In the first position itself, we get 1. So, write that one as it is here. After that first one, just take the complement of all other bits. So this 0 become 1, this 1 becomes 0, this 1 becomes 0, this 1 becomes 0. So this is the 2's complement of the given number. Okay, so now just analyze the options. Here all the options are with 8-bit. That means we need the solution in 8-bit form. Here we get a result with 1, 2, 3, 4, 5-bit form. We need to make this in 8-bit form. One important property of our 2's complement representation is that we can add any number of 1 to the left end. It will not change the value of the number. Once more, if we add 2, 3 or any number of 1's to the left end of a 2's complement number, it will not change the value of that number. In a normal binary number, we can add any number of zeros to the left end. It will not change the value of that number. Just like our decimal. Right? But here in 2's complement representation, instead of 0, we can append any number of 1's to the left end. It will not change the value of that number. So, in order to make this 5-bit representation to 8-bit representation, we can append 3 more 1's to the left end in the 2's complement form. So, which option is the right answer? Option 1 is the right answer. Okay, next question. The 2's complement representation of minus 539 in hexadecimal. 539 is given in decimal form. We need to get the 2's complement representation of it, and the options are in its hexadecimal form. Okay, one method is we can convert this directly into its binary form. The number is actually a negative number. To get its binary equivalent, we can take the binary of positive 539. Then take its 2's complement. That will equal to the binary representation of our minus 539. Okay, we can divide this continuously using the divisor 2 and take the binary representation of positive 539. Then take its 2's complement form. That will equal to the 2's complement form of our, or the binary form of our minus 539. Right. Here actually I did this division, that is division using base 16. Divisor is taken as 16. This is also possible. We can divide this 539, positive 539 using 16 continuously and generate an hexadecimal equivalent of this positive 539 as 2111 in hexadecimal using symbol B. Okay, 21B to the base 16 is the hexadecimal representation of positive 539. So this hexadecimal number, we can directly convert this into its binary equivalent. That is, B can be represented as 1101. Sorry, B can be represented as 1011 using 4-bit representation. 1 can be represented as 0001 and 2 can be represented as 0010. This is also a different method for getting the solution of this question. In another way, we can divide this 539 using the base 2 continuously and directly generate the binary form. Then it will generate the binary pattern corresponding to positive 539 and take the 2's complement of that. It will gives the exact result. Here I have done like this, that is division using 16 and generate the hexadecimal equivalent and take its binary form. Taken its binary form. Okay, now we need to take its 2's complement in order to get the binary representation of minus 539. This is actually the binary representation of positive 539. Right? We can take its 2's complement. 1/3 is 1's complement plus 1 gives the 2's complement form, that is equal to minus 539. Another method is, as we have already discussed in our previous example, start from the right hand, proceed towards left and write everything as it is up to which the first one is encountered and take the complement of all other bits after that first one. That means this one is write it as 1 itself here and this one becomes 0, this 0 become 1, 0 0, 1 1 1 1 0 1 1 like this. Okay, so here options are in its hexadecimal form. We need to convert this binary pattern to its equivalent hexadecimal form like this. This start from the right hand and make different groups of 4-bit. So 0 1 0 1 for the LSB group, which is equal to 5. Next is 1 1 1 0, which is equivalent to hex value E. Next is 1101, which is equivalent to hex value D. So option C is the right answer. Okay. So next question, given a number P. P is a 16-bit signed integer. 16-bit signed integer. The 2's complement representation of P is given in hexadecimal form. P is a signed number. Here we are following the 2's complement system. 2's complement system of representation. So the 2's complement form of P is represented here using its hexadecimal equivalent. The 2's complement representation of 8 into P. We need to get the 2's complement representation after this multiplication. Okay. So P is like this. So first step is take its binary equivalent. 2's complement of P is given like this. Okay. And its binary equivalent is like this. P means 1011, 7 means 0111, 8 1000, F 1111. So this is actually in 2's complement form. which is already mentioned in our question. So from this pattern, it is clear that MSB bit is 1. That means the number is negative. Okay, and a 2's complement representation of binary numbers, if the MSB bit equal to 1, that means the number is negative. If the MSB bit of a binary in 2's complement representation is 0, that means the number is positive. Here the MSB bit 1, that means B is negative number. So 8 into 8 means decimal 8. So positive 8 into a negative number means result is again negative. Okay, so one method is we can take its decimal equivalent, then multiply with 8 and get the decimal equivalent product value, convert back into its binary form or convert directly into its hexadecimal form. Here we can follow a simple method, that is, this binary we can multiply directly using the 2's complement of 8. This 8 is actually in its decimal representation. We need to take its 2's complement. So now this 8 become 2's complement form. P is already in its 2's complement form. So two numbers in the same representation, now we can multiply. How to get the 2's complement of 8? First take the binary of 8, that is 1000. Its 2's complement is 1000 itself. Why? Based on our previous method, take the 2's complement of this 1000, that is start from the right hand, proceed towards left and write everything as it is up to which the first one is encountered. Here the first one is present in the MSB position. So everything is right as it is. So the 2's complement of binary 8 is 1000 itself. Okay, now we can multiply directly this binary form with the 2's complement of 8, that is 1000. Here only single one is present in this multiplier. So the multiplication is very simple. Just appending 3 more 0 to its right hand. Right? In order to get the product of this multiplication, what we want to do here, only MSB bit is 1. All others are 0. So while multiplying this, write these bits as it is here, append 3 0 to the right hand. So this is the result of our 8 into P in 2's complement form. So the options are in hexadecimal form. So we can make different groups of 4 bits from right hand and proceed towards left and assign its hexadecimal equivalents. So the first is 1000, which is 8. 1101, that is D. 0011 is 3. 1100 is C. Okay, but here 3 ones left over here, right? But all the options are with 4 simples, right? So we need to remember one point. In 2's complement representation, if the MSB bit is 1, then we can append any number of 1s to the left hand. It will not change the value of that number. Similarly, in a 2's complement representation, if the MSB bit is 0, then we can append any number of 0 to the left hand. It will not change the value of that given number. That means appending 1 means the number is already negative. In that case, the MSB bit become 1 in 2's complement representation. That case, we can append any number of 1 to the left side. It will not change the result. Similarly, if the MSB bit of a 2's complement representation is 0, that indicates that result or that particular number is positive. In that case, we can append any number of 0 to the left hand, it will not change the result. So here already the MSB bit is 1. So here we have 3 more 1s available here. We can simply discard this 3 more 1s. Okay. So based on this option A is the right answer. If we want to consider these 3, or if we want to include these 3 ones also in our result, we can append one more 1 here. Then it become F in hexadecimal form. So in that case the result become FC3D8. Okay. Thank you.